So solubility equilibrium is really just an application of what we have just done. Okay, so last year we did a unit on solutions and solubility. We determined whether something was soluble or insoluble. And so last year we would have said when you had a double displacement reaction, so something like this, it was very common for one of the reactants to have an alkali metal. The reactants had to be aqueous, and so sodium here is going to be an aqueous ion. That was a very common thing. Nitrate was a very common aqueous anion we saw in many problems. And then something like silver, which is a big cation, is often going to produce a solid. But you didn't have to guess. You didn't have to memorize. You looked it up. So the two reactants were given to you as aqueous, and then we switched the partners. Anything plus sodium or nitrate plus anything is aqueous. And then chloride plus silver is insoluble. And we said insoluble meant solid. We only did this qualitatively. We didn't do any further calculations because that's what we're going to do this year. So after we predicted which one was the solid, then you had to think about what kind of ions came to the event but didn't participate. So sodium and nitrate, what do we call ions that are aqueous on both sides? Starts with an S. Spectator ions, good. So sodium we canceled out, nitrate we canceled out, and then so the solid is formed by the cation silver and the anion chloride to get silver chloride, okay? So because we only did this in qualitative terms, could you see a precipitate or not, then that was as far as we went. However, if you actually calculate the concentrations, then what you can find is we can sort of get something that is said to be qualitatively insoluble. We can get it to dissolve a tiny, teensy-weensy little bit, okay? And so that's what we're going to do this year. We are going to look at where we are going to force something that we would have qualitatively said was insoluble. We're going to get it to dissolve a very, very small amount. So unfortunately, those of you that don't love scientific notation are not going to have a choice here. So we're going to have numbers like 1.5 times 10 to the negative 13, and there's no way to put that in your calculator. The display will not hold enough digits to give you that small of a number. So we are looking at the category of insoluble where it's going to be less than 1, a very, very small number. And so what it matters for us in or why we're going to call it solubility is because when you have a soluble solid, then it totally, completely dissociates and makes ions. So something like hydrochloric acid is going to completely dissociate. The formula HCl together doesn't really exist because it's so soluble in water that equilibrium would not be established. So when you have something that we would have said was insoluble, that is where you're going to get the KSP, or the solubility product constant, or the solubility equilibrium constant. But it's calculated the same way as KQ. No solids or liquids, no units. Coefficients are exponents. We're going to use concentration values. The ratio is still products over reactants. Okay? So next week when we do applications, we'll still look at what happens when one side is favored over the other, how can we get the equilibrium to shift according to Le Chatelier's principle. So we're going to do all that stuff again, just in terms of a solubility equilibrium. So when we did the intro stuff, we did quotient because the answer to division is called a quotient. So why is the solubility equilibrium constant called a product? So what we're going to use as our equilibrium system is the dissociation equation. So one of the differences in this section is that you are going to have to write the dissociation equation. We did that in grade 11, okay? So and when you're doing a dissociation equation, it's going to be for an ionic compound, which follows the crisscross rule. So there really isn't that many crazy things that can happen. But the big ideas are that the solid is always the reactant and the ions are always the product. So that's going to matter when we do products over reactants. And if you forget, dissociate means break apart. So last year we canceled out the spectator ions, you showed the formation of the solid. Then when we got to stoichiometry of solutions in unit 4, then you had to do dissociation equations, okay? So just like grade 11, I'll give you the formula of the solid, okay? So the solid is always going to be the reactant. We're going to draw an equilibrium arrow. Most people go in order of the ions as given. So, for example, we say sodium chloride, not chlorine sodiumide. We always put the metal first. But it doesn't really matter. So usually people will go in the same order. So the cation and the anion. And I'll give you what the solid is. Okay, so you don't have to remember what the crisscross rule. Yes, you have a periodic table with the polyatomic ions on it, but I'm not going to, we did that enough in grade 11, okay? So you just have to split it apart into the ions. There are some things that are going to make our solubility lives easier. So the solids coefficient will always be 1. And because you have to follow the crisscross rule, the charges will be 1, 2 usually. Maybe a weird one could have a charge of 3, or maybe if I gave you a weird transition metal that has weird charges, there could be a 2 or a 3 or a 4. But there really isn't a lot of variety. Okay, so the exponents and the coefficients will not be too crazy. So when you have an equilibrium system that contains an insoluble solid dissolved in water, insoluble I put in quotations, then when you establish equilibrium, what that means is no more solid can be dissolved, which is the definition of a saturated solution. So one of the different things about this section versus the intro section, it always said initially the scientist puts in however many moles per liter, blah, blah, blah. At equilibrium, it's measured to be this, or calculate what it is at equilibrium. And in this case, it could use the words solubility instead of saying at equilibrium. It could say in a saturated solution, which means at equilibrium. So it is a little bit different. So this is also saturated solution is also a definition from grade 11, but let's just rewrite it or remind ourselves. Last year we did grams per milliliter, we did ppm, ppb, we did percent mv, vv, all that stuff. We're going to focus on concentration in molarity, moles per liter, because we are using, when you do the change line in the ICE table, if you're trying to use the same X value, then essentially what we're doing is stoichiometry, so you have to have molar values. So you don't have to worry about any of those other, like no solubility curves, none of that. Okay? And when you have a question and it talks about the maximum amount of solid that can be dissolved, or the amount in a saturated solution, or, you know, this is the solubility, all of those mean the same things, and those concentrations go in the E line of the ICE table. And really what you're going to see today, by the time we do all the examples, you'll be like, why do we even have to do an ICE table? They're a little bit simplified because the solid's always on the left. It's the application part of it next week that the basics have to be down so that when you have to manipulate the ICE table a little bit, you're ready to go. Okay, so let's just talk a little bit about the equilibrium law first before we do ICE problems. Okay, so if we have our example, we have silver chloride goes on the left, the cation goes first, and the anion goes second. So when you were in grade 11, I said you had to write AQ for the ions. I didn't say you didn't lose marks if you didn't write the charges. That was okay. But one of the big things from grade 11 as well is that chlorine, for example, is a special type of element. What kind of element is chlorine? What do we call it? I heard someone say it. Diatomic. So when you have chlorine in a synthesis reaction, decomposition, single displacement, something like that, you could make chlorine gas, Cl2 gas. Is this chlorine gas? No. Okay, so it is not going to be Cl minus 2. That is not the elemental form of chlorine. So last year we really tried to make sure that you wrote the AQ part of it to emphasize that those are ions. So when you write the equilibrium law, products over reactants, coefficients are 1 because, and then so the exponents are 1. Am I going to include solids in the equilibrium law? No. Okay? So technically, there is no bottom to our ratio. So now we are no longer dividing, we are multiplying. So what's the answer to multiplication called in general? Product. Okay, so that's why it's called solubility product. So instead of just KS, we call it KSP. Every single question will look like this. Every solid has a positive and a negative, okay? So you're going to have two terms in your solubility product constant. That's it. So then one of the reasons, even though I'm going to give you the formula of the solid, if you were, I'm just going to skip for 2 seconds, say something like this, where it has a polyatomic ion. If that really frustrated you in grade 11, then use this table to help you, because you're not going to split apart the polyatomic ion. It will be on the product side as the anion. The only positive polyatomic ion is ammonium, and ammonium is never insoluble, so it's not going to be one of the solids, so you don't have to worry about that. It could be that the anion is a polyatomic ion, okay? So if you hated polyatomic ions, check your sheet. If you were the kind of person that even if it was a 1, you liked brackets, put the brackets in, okay? So the equilibrium law part of it is not so bad. Even next week when we do applications, what's going to be tricky is trying to decide where do our values go, okay? So we are going to do problems today where the initial amount of ions is 0. And what it's like you have a solid, and we would have said nothing dissolves. So initially you have 0. If we are allowing the equilibrium to be established, then you get some ions. So then the molar solubility, or the maximum amount that will dissolve, is going to be at equilibrium. So it could say blah, 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 saturated solution, that goes in the E line. If it talks about molar solubility, these values also go in the E line. So I included these 2 points here because last year we did a bunch of ways to find the maximum amount that can dissolve, but we're going to focus on molar. We need to be able to do stoic, so it's going to be either moles per liter or big M, just like the intro section. So the more that can dissolve, or the more soluble the solid is, the greater the solubility. So today, we'll do an example where, again, when we do the math, you'll be like, holy cow, Ms. Todd, this is easy. But then next week, you'll be able to compare solids. Which one will precipitate first? Which one with a common ion will have, will be less soluble, and all kinds of stuff, okay? So today's easy questions, or if you do them, after the test tomorrow, then they will help you feel better about next week. And so we're going to do similar to the intro unit as well. We're going to do 2 types of questions. One where you're given the K value and you have to solve for X. And the other one where you're given the X value, or you're given something at equilibrium and you have to solve for K. Okay? So sometimes students will mix it up. Again, unfortunately, the numbers are going to be weirdly very, 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 very tiny. Okay, so let's just practice writing the KSP, or the equilibrium law expression first. So again, when you have something like, actually all of them have an anion, that's a polyatomic ion. If you would like, you can put the brackets in, okay? Because you will have to write your own dissociation equations in order to build your ice table. Okay, so what I did was a cation, actually, some cations with the coefficient, so the exponent. Just like always, if you have a charge in the top right-hand corner, that does not affect the balancing. It does not affect the number of atoms. Every single dissociation equation, the solid's coefficient is 1, okay? But we are not going to include the solid because they don't belong in the solubility law. Okay, so silver, Ions have a coefficient of 2, so their exponent is 2. Chromate is the anion. It is a polyatomic ion. It is on the back of your periodic table. It also has it does have a coefficient of 1, so its exponent is 1. And when you have ionic compounds, they are very boring and rigid and follow all of the rules. So when we crisscross barium's charge of 2 and chromate's charge of 2, those 2's are reduced or canceled out. So we're left with coefficients of 1 and 1. Okay, and phosphate is the only polyatomic ion that we focus on that has a charge of 3. So in this case, it's made the silver have a 3. So the exponent is 3. All right, so let's do a math question. So the molar solubility of AgBr in pure water is 7.1 times 10 to the negative 7 moles per liter. What is the KSP for the salt? So this question talks about pure water. And again, that's unfortunate, but because we don't need the water part of it, what that means is it's going to form aqueous ions. You get the formula of the solid, AgBr. You have to write your own dissociation equation. And then you have to decide where does the 7.1 times 10 to the negative 7 go, okay? So, when you do the problems, even though at first it's like, it doesn't say equilibrium anywhere on there, and that can be annoying, they are going to be very, 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 very similar, okay? So molar solubility, again, that means the maximum amount of solid that dissolves. So you have to know that means that that goes at equilibrium. You're asked for the KSP, or in the other type of problem we're going to do, you would be given KSP, so remembering that K means equilibrium as well is important here. So it doesn't even say use an ice table or anything like that. So again, the wording here sometimes can be hard to get used to because it's a little bit different than the first chapter. Okay, so AgBr, Ag is a charge of 1, Br has a charge of 1. So when they crisscross, there is no coefficient. So no exponent. And it's always S ion plus ion. Most people just do the cation first because, again, we always put the cation first in the equation. We don't say bromine silveride, right? We always put the metal first. But if you flipped it around, that doesn't matter. So this is our equilibrium system. When you have an equilibrium system and you want to solve a quantitative problem, you need an ice table. And this is where the wording matters. So are we going to have a solid in our equilibrium law? So cross it out. And now we need to fill in the other side. So again, what we're thinking of is last year we would have said AgBr is insoluble. So why are we now showing that it can dissociate? So initially we would have no ions. Or just like last time we said, okay, if it didn't tell us anything about the initial concentration of a substance, product, or reactant, you would have put 0. But then in the previous problems, it would have said at equilibrium, this is the concentration. Here it doesn't say that, but it does say molar solubility. So you have to know that the molar solubility means at equilibrium. Okay, so equilibrium means it has to go in the E line. What letter do I use in the change? X. And so just like last time, if this is 0, can the concentration become negative? No. So it has to be plus. Same thing like 0 plus X. So you could, if your strategy in the first chapter of this was to do the ice table and then figure out, are you given K or are you given X? You could do the same thing here. So now we are asked for KSP and we're given the molar solubility. So I just told you the value goes in the E line. It technically says the molar solubility of AgBr. So AgBr is here. Okay? 7.1 times 10 to the negative 7. But if we cross out the solid, isn't that value useless? And this is where it matters, and this is why we're only going to use moles per liter. So according to stoichiometry, if this has a coefficient of 1 and its concentration is 7.1 times 10 to the negative 1, or 7, sorry. If I did a ratio and this coefficient was also 1, stoichiometrically, these two things would be the same. And this would be the same as this as well because it's all 1 to 1 to 1. So we're going to use molar solubility because you can write a ratio, or you can just streamline the stoichiometry process. So we did examples of this in grade 11 as well. Okay, so if you do how many moles per liter is silver, and in the bottom you put a 1, and then over here I put AgBr, and its coefficient is 1, is this number going to change? No. Okay? So if this is 7.1 times 10 to the negative 7, this has a coefficient of 1, and so is this. And so is this. Yes. This X? Yes. So after you do even a few of these questions, you probably wouldn't even write it in here. You would just write it in here. You wouldn't even worry about 0 plus X. It's going to be the same thing every single time. You either have a molar solubility and you put it in the E line, or you have a K and you have to solve for X. Okay? Mathematically, these initial problems are very straightforward. There is not a lot of variety. The biggest issue will be, we're going to do one where it's going to have a coefficient of 2, so then you would have to multiply by 2, okay? Not a big deal. But you can do the ratio every time to prove it to yourself for sure, okay? So now I'm going to do KSP. Just like last time, you get marks for the equilibrium law, so write it out. There are definitely mathematical ways you could streamline this question. If you have the same value, technically that would be squared. That's fine. Does K have units? No units, okay? That is a tiny, tiny, tiny number, so you definitely need to know how to use scientific notation. Did you use the paper at all? All good? No questions? Awesome. Great job, Ken. Actually, let's write that down. No units. There are definitely things you can do every single time. You don't have to write this stuff on the right-hand side here, but you will get marks for an ICE table. You will get marks for writing the equilibrium law. So make sure you don't show too little work either, okay? Bless you. Okay, so we'll do another one. This time it's the same format. Molar solubility is whatever. What's the KSP? But I wanted to show you one that has a 2, okay? So write down the formula of the solid, dissociate it. Decide for yourself. I do not like polyatomic ions. I need to put brackets. Okay, whatever works for you. So there are 2 silver ions. The 2 becomes the coefficient, okay? Just like grade 11. Okay, so we're going to do the same thing. ICE, cross out the solid, 0, 0, plus 2x, x. And then decide, I would like to have the same format for every ice table. I'm going to write 2x and x first, and then I'm going to think about what else am I given? Do I solve for x? Am I given a molar solubility value? That's really up to you, okay? You can do the same format for every word problem or every ice table, and then go back and read carefully if you would like. Okay, so it says the solubility of silver chromate is 6.7 times 10 to negative 5. Again, you don't have to write it over there. If you don't want to, you can plug it right in. So that means that this value, the x value, is 6.7 times 10 to negative 5. But because there are 2, there's a coefficient of 2 in front of the silver, we have to multiply that by 2 according to stoichiometry. And if it touches your dark side to streamline stoichiometry like that, you can do the ratio. How many moles per liter of silver, if its coefficient is 2, when we have 6.7 times 10 to negative 5 silver chromate, and its coefficient is 1. So you would be multiplying by 2, okay? And the reason we can do this, even in grade 11, was because the coefficient on the solid always will be 1. So it's always going to be over 1, and then whatever this is, usually a 1, maybe a 2, maybe rarely a 3, then you would just be multiplying, okay? when you plug the value for silver in ions into the KSP, it also has to be squared. So don't forget to do that as well. So yes, multiply by 2 and yes, square. If you are a scientific notation lover and you want to write 0.000134 as scientific notation, whatever, okay? You can certainly input that into your calculator as one step. You just have to make sure to follow the bed mass, that you're squaring the 0.000134 first, and then multiplying by 6.7 times 10 to negative 5. So if you use brackets, it'll work. You could, even if you have an answer button, that's very helpful. Do the squaring, push equals, and then multiply by the answer. Please don't forget, when you have a scientific notation number, you can't just write down 1.2, or 1.20. The times 10 to the negative 12 is vital. And especially in this case, that means 0.11 zeros and then 1, 2. That is a very, 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 very small number. So we are using that to say, okay, last year, yes, qualitatively we would have said insoluble, because the amount, if you can't calculate it, your grade 11 brain wasn't big enough, then now when you can calculate it, it's a small number. Is it too small? You know, that's what we're going to look at next week. When is it too small? When does a precipitate form? Yes. Yes. Okay, so let's do the other kind of problem. What happens when you're given KSP and you have to solve for X? So we did one example where the solid had the two ions had coefficients of 1. We did where the cation has a coefficient of 2. Now we're going to do what happens when the anion has a coefficient of 2. And it's very, very similar, okay? But we are this time given the KSP value, and we're finding or calculating the molar solubility. So the molar solubility goes in the E line. So this time we don't have X. We are calculating X. But the general structure is the same. I give you what the solid is, and you split it apart into ions. Okay, and this is one, especially this kind, that is very, 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 very annoying. Because it looks like, it's like, oh yeah, iodine is diatomic. It's one of the 7, right? So that's why the little 2 is there, but it's not. The little 2 comes from crisscrossing with the silver, the lead, Pb. So what that means is we have to write iodide ions. And how many ions are there? 2. In fact, not only is it not the diatomic form, none of them ever will be. That means gaseous diatomic molecules, that's not what we're talking about here. Dissolving in water makes aqueous ions. So last year, if you were ever like, "Ugh, why is she forcing us to write the aqueous? What does it matter?" This is why it matters, okay? Because if you put I2, a subscript of 2, the coefficients will be 1, the exponent is 1, and now your equilibrium law is messed up, okay? But this is all the same, ice table the same, cross out the solid, 0 lead, 0 iodide, plus x, because the coefficient is 1, plus 2x, because the coefficient is 2, x, 2x. So same ice table every time. But in the other versions of the questions, we could write down the moles per liter, solve for, use that to input x, and calculate KSP. This time we're given KSP, so we can't do that. So sometimes it's annoying because it's tricky to tell which is which. When you're given the KSP, it's not going to say moles per liter or big M, so there's no units. The X value has to be moles per liter. So I'm going to plug that in over here. When you do 2x squared, you square the 2 and square the x. If you multiply by a base that is the same, what do you do with the exponent? Yes. Yes, you're going to get 4x cubed. Okay, so which is doable, we can solve for x, but it's weird. When you do inverse operations, you have to invert BEDMAS as well. So we're actually you have to divide by 4 first and then take the cubed root. Now, many calculators have a cubed root button, so you can do again, as one step, do this divided by 4 and then take the cubed root of the answer. It's really up to you. But you have to make sure that you're doing the proper math. You have to divide by 4 first. And last time, when we took the root, you had to take a look at both solutions, the positive and the negative. But because we want this to be, the x value is just going to be the x value, then we don't want the negative. So we can just take the positive root, but we have to cube root. So if your calculator does not have a cubed root button straight up, then what you have to do is use the other one that has like a blank, and then you push 3 and that button, and then the answer you're trying, or the number you're trying to cube root. When you have this as an answer, this is actually okay. I would accept this. However, molar solubility has to be moles per liter, okay? So you either have to attach units to your x value, or maybe you would prefer to write an answer statement, okay? because normally we don't attach units to the x value. So if you would like to be as concise as possible, just make sure your answer does have units, okay? Okay, and then the last type of problem, actually today, you don't even really have to do any math. However, next week, when things are more complicated, then you could have to do math. Or if these are both one cation, one anion, one cation, one anion, so they can be directly compared. If not, then you would have to determine what the x value is. So if you have a question, it asks you which solid has a greater solubility, which solid has a less solubility next week, which solid precipitates first, then what you can do is look at the x value. So the x value is the molar solubility, which means that if you have a bigger x value, then the more soluble the solid is, okay? So when you get a really simple question like this, if you built an ice table for either of these solids, you would have one cation and one anion. So to solve for x, all we would do is square root. So again, if you do not have a lot of, what's the word I'm looking for, experience with scientific notation, sometimes the scientific notation number can be misleading. Usually, we think of exponents to increase a value. But when it's a negative exponent, what that means is more zeros. So this number is actually significantly smaller than this number. It would be 0.8 zeros, 1, 2, 2, whereas this one would be 0.3 zeros and then 4, 1. So this number is actually quite a bit bigger, 10 to the power of 5 bigger than this one. Okay, so the greater the x value, the more soluble the solid is. When it's all 1, 1, 1, then you could just take a look at the KSP. But if it's not 1 to 1, you would definitely have to solve for x. Okay, so CuCl has a greater X value. It has a greater molar solubility.